Right now, as you watch this, something is protecting you. You cannot see it, you cannot feel it. You have never once been aware of it in any direct sensory way. But without it, you would not be alive. Not because of anything dramatic, not a single catastrophic event that you would have noticed and named, but because without it, the sun would have stripped away Earth's atmosphere over millions of years, cosmic radiation would have made complex life impossible, and the chain of biological events that produced you would never have started. It is Earth's magnetic field, and it is failing. Not catastrophically, not suddenly, but measurably, consistently, in a direction that has been confirmed by every geomagnetic observatory on Earth for the last 170 years. The magnetic field is weakening. At its current rate of decline, approximately 5% per century, it has lost roughly 9% of its strength since systematic measurement began in 1840. The South Atlantic anomaly, a region of dramatically weakened field over South America and the South Atlantic, has been growing and intensifying for decades. Satellites passing through it experience increased radiation exposure. The International Space Station adjusts its orbit to minimize time spent in it. And the magnetic poles are moving. The North Magnetic Pole, the point toward which a compass needle points, has been drifting toward Siberia at an accelerating rate. In 1900, it was in northern Canada. By 2020, it had crossed the international dateline. It is moving at approximately 55 kilometers per year, faster than at any point in the recorded history of geomagnetic observation. These measurements are not alarming in isolation. Geomagnetic variation is normal. The field has always fluctuated. The poles have always drifted. What makes the current situation different is what the geological record shows happens when the drift accelerates, the field weakens, and the poles begin moving erratically. It shows a reversal, a geomagnetic reversal, an event in which the north and south magnetic poles swap positions, has happened approximately 183 times in the last 83 million years. It is a normal feature of Earth's geological history. It has happened before, it will happen again. What is not normal, what the geological record does not clearly resolve, is what happens to life on Earth during the reversal. Because during a reversal, the magnetic field does not simply flip cleanly from one orientation to the other. It weakens, it becomes chaotic. Multiple poles appear at different locations simultaneously. The protective shield that currently deflects most of the solar wind and cosmic radiation becomes, for a period that may last anywhere from a few centuries to tens of thousands of years, dramatically compromised. The last full reversal happened approximately 780,000 years ago. It is called the Matuyama-Brunnis boundary. We were not there. We have no direct record of what happened to life during it. What we have are proxies, and some of those proxies are disturbing. In this video, we are going to go through exactly what a geomagnetic reversal is, what the current measurements tell us about where we are in the cycle, and what the best available science says about what happens to a technologically dependent civilization when the magnetic shield fails. There is something specific in the third section of this video that most people find the most alarming. Not the reversal itself, but a detail about the timeline that the mainstream coverage consistently omits. It reframes everything about how urgent this is. Stay with me. Before we go further, the North Magnetic Pole has moved more in the last 50 years than in the previous 200 combined. Drop a comment if you knew that before watching this. Most people don't. And the reason they don't is in the next section. To understand what a geomagnetic reversal means, you first need to understand what the magnetic field is and where it comes from. Earth's magnetic field is not a permanent magnet. The planet is not magnetized the way a refrigerator magnet is magnetized. The temperature deep inside the Earth far exceeds the Curie point, the temperature above which magnetic materials lose their permanent magnetism. Below the Curie point, iron and nickel align their magnetic domains and become permanently magnetized. Above it, they do not. Earth's core is far above the Curie point. The inner core, a solid sphere of iron and nickel, approximately 1,220 kilometers in radius, is at a temperature of approximately 5,000 to 6,000 Kelvin. The outer core, a liquid shell of iron and nickel, approximately 2,300 kilometers thick, surrounding the inner core, is at temperatures between 4,000 and 5,000 Kelvin. At these temperatures, permanent magnetism is impossible. And yet Earth has a magnetic field, one that has persisted for at least 3.5 billion years, as evidenced by the magnetic signatures preserved in ancient rocks. The field is generated not by permanent magnetism, but by a process called the geodynamo. The liquid outer core is in constant convective motion, driven by heat from the inner core and from the decay of radioactive elements, and modified by the Coriolis force from Earth's rotation. This convection causes the electrically conductive liquid iron to move in complex, organized patterns through the existing magnetic field, generating electric currents that in turn generate and sustain the magnetic field. The geodynamo is self-sustaining. The motion generates the field influences the motion, and the system maintains itself as long as the heat flow from the core continues to drive convection. But the geodynamo is not simple. The convection patterns in the outer core are turbulent, three-dimensional, and constantly changing. The magnetic field they generate is not a perfect dipole, not a simple north-south bar magnet. It has higher-order components. It varies in intensity over different parts of the globe. It drifts and shifts over time as the convection patterns evolve. The north and south magnetic poles, the points where the field lines are approximately vertical, are not fixed points. They move continuously as the underlying convection patterns change. Under normal conditions, this movement is slow, tens of kilometers per year, roughly following the geographic poles. What makes a reversal different is not the existence of pole movement, but its character. During a reversal, the convection patterns in the outer core undergo a fundamental reorganization. The dominant dipole component of the field, the north-south orientation that has characterized Earth's field for the past 780,000 years, weakens dramatically and becomes disorganized. Multiple poles appear at different locations. The field becomes quadrupolar or multipolar, more complex, weaker, and less protective. This transition from a stable dipole to a chaotic, multipolar state is what constitutes the reversal process. And it is during this transition, not at the moment of the pole swap itself, that the field is most compromised. The geodynamo mechanism was first proposed by Walter Elsasser in 1946 and Joseph Larmor in 1919. Modern computational models of the geodynamo, including simulations run at the National Center for Atmospheric Research, have successfully reproduced spontaneous magnetic reversals in numerical models of the outer core, confirming that reversals are a natural consequence of the fluid dynamics of the liquid iron core rather than requiring any external trigger. The geological record of past reversals is preserved in a remarkable natural archive, the ocean floor. When magma erupts at mid-ocean ridges and cools into new oceanic crust, the iron minerals in the cooling rock align with the ambient magnetic field and freeze in that orientation. As the oceanic crust spreads outward from the ridge over millions of years, it preserves a continuous record of the magnetic field's orientation at the time of its formation. This record, first systematically analyzed by Vine and Matthews in 1963, shows alternating bands of normally and reversely magnetized rock stretching symmetrically away from mid-ocean ridges across the ocean floor. Each band corresponds to a period when the magnetic field had a specific orientation. The boundaries between bands record reversals. From this record, geologists have reconstructed the history of geomagnetic reversals going back hundreds of millions of years. The result, called the geomagnetic polarity timescale, shows that reversals are irregular in timing, ranging from a few tens of thousands of years between reversals to many millions of years of stable polarity. The current period of stable normal polarity, the Brunhes normal chron, began approximately 780,000 years ago with the Matuyama-Brunhes reversal. At 780,000 years, it is significantly longer than the average chron duration of approximately 200,000 to 300,000 years. This does not mean a reversal is overdue in any deterministic sense. Geomagnetic reversals are not periodic. There is no clock. But statistically, the current chron is on the longer side of the distribution, and the current measurements of field weakening and pole acceleration are consistent with the early stages of a reversal process. Let's talk about what is actually being measured right now, because the numbers are more specific and more striking than most coverage suggests. The systematic measurement of Earth's magnetic field began in 1840, when Carl Friedrich Gauss developed the first quantitative method for measuring field intensity. Since then, a global network of geomagnetic observatories has tracked the field continuously. What that 180-year record shows is a field that has been weakening at a rate of approximately 5% per century. The total dipole moment, the overall strength of the field, has decreased by approximately 9% since 1840. If this rate continues, the field will reach zero, complete field collapse, in approximately 1,600 to 2,000 years. That extrapolation is not a prediction. The field does not behave linearly. It fluctuates. It may stabilize. It may weaken faster. Historical reversals show that the field weakening during a reversal is not a smooth decline, but a complex, irregular process with periods of acceleration and partial recovery. But the direction of the trend is clear, and it is accompanied by structural changes that are more diagnostic of a reversal in progress than the overall weakening alone. The South Atlantic anomaly is the most visible of these structural changes. It is a region of dramatically reduced field strength, approximately 30% weaker than the global average, centered over South America and the South Atlantic Ocean. It has been present in geomagnetic measurements for at least 400 years, when Portuguese navigators first recorded compass anomalies in the region. Over the past century, it has been growing. It has been intensifying. And recent satellite data suggest it may be splitting, developing a second intensity minimum over the southwestern Atlantic that could indicate the early formation of a new magnetic pole in the southern hemisphere. The South Atlantic anomaly is not an artifact of measurement. It is a real feature of the field, and its location, its growth, and its potential splitting are consistent with the behavior of the field in computational models of reversals in progress. The movement of the North Magnetic Pole tells the same story from a different angle. In 1831, the British explorer James Clark Ross located the North Magnetic Pole in the Canadian Arctic at approximately 70 degrees north, 96 degrees west. For most of the subsequent century and a half, the pole drifted slowly southward and westward within the Canadian Arctic, moving at rates of 10 to 15 kilometers per year. In the 1990s, the drift accelerated. The pole began moving towards Siberia at increasing speed. By the 2000s, it was moving at approximately 40 to 55 kilometers per year, 3 to 4 times faster than its historical average. By 2020, it had crossed the international dateline and was approaching the Siberian coast. This acceleration was sufficiently significant that the World Magnetic Model, the mathematical model of Earth's magnetic field used by navigation systems worldwide, including GPS, aviation autopilots, and smartphone compass apps, had to be updated outside its normal 5-year revision cycle. An emergency update was issued in February 2019, ahead of the scheduled 2020 revision, because the pole was moving faster than the model had predicted. Your phone's compass was updated in an emergency because the magnetic pole was moving faster than expected. That is the current situation. The acceleration of the North Magnetic Pole's movement towards Siberia is thought to be driven by a jet of liquid iron flowing rapidly beneath the core mantle boundary under the Arctic, a geodynamic feature that is pulling the magnetic pole in its direction. This jet is a feature of the complex, turbulent dynamics of the outer core, exactly the kind of dynamic that computational models associate with the early stages of a reversal. The World Magnetic Model is maintained jointly by the British Geological Survey and the National Oceanic and Atmospheric Administration. The emergency update issued in February 2019 corrected for the unexpectedly rapid movement of the North Magnetic Pole, which had exceeded the model's error tolerance of 1 degree. The pole's acceleration was attributed to a high-speed jet of liquid iron in the outer core beneath the Arctic, identified using data from the European Space Agency's SWARM satellite constellation launched in 2013. The SWARM constellation, 3 satellites launched by the European Space Agency in 2013, specifically to monitor Earth's magnetic field with unprecedented precision, has provided the most detailed picture of the field's current state ever obtained. What SWARM has shown is a field that is not weakening uniformly. Some regions are weakening rapidly, others are strengthening. The South Atlantic anomaly is the most prominent region of weakness, but there are other areas of reduced field strength appearing at high latitudes in both hemispheres. More significantly, SWARM data has revealed patches of reversed magnetic flux on the core mantle boundary, regions where the field is oriented opposite to the dominant polarity, as if small sections of the field have already flipped. These reverse flux patches are growing. They are concentrated under the South Atlantic, consistent with the anomaly, and under the Arctic. Reversed flux patches on the core mantle boundary are exactly what computational models of reversals show during the early stages of the process. They represent the leading edge of the reorganization of the convection patterns in the outer core that eventually produces a full reversal. This does not mean a full reversal is imminent. The timescales involved are geological, potentially thousands to tens of thousands of years. The current measurements could represent a failed reversal, an excursion in which the field weakens, becomes chaotic, and then recovers to its original orientation without completing a full pole swap. Excursions are documented in the geological record. The Lachamps excursion, approximately 41,000 years ago, saw the field weaken to approximately 5% of its current strength, and the poles temporarily relocate to near equatorial positions before recovering. It lasted approximately 1,000 years. Whether the current geomagnetic changes represent the beginning of a full reversal or another excursion cannot be determined from current data. The distinction matters enormously for the consequences, but it cannot be determined. We do not have the predictive capability. The Lachamps excursion is the most studied geomagnetic event in the recent geological record. It is also the event that changed the conversation about what happens to life and to civilization during a period of dramatically weakened magnetic field. Approximately 41,000 years ago, Earth's magnetic field underwent a rapid weakening and disorganization. The dipole field collapsed to approximately 5% of its current strength. The poles moved to near equatorial positions. The North Magnetic Pole was located near the current geographic equator for a period of approximately 250 years. The event lasted approximately 1,000 years in total before the field recovered to a stable, normal polarity. For most of the 20th century, the Lachamps excursion was a geological curiosity, documented in the paleomagnetic record, studied by specialists, largely unknown outside the geoscience community. That changed in 2021. A paper published in Science by Cooper and colleagues, analyzing records from tree rings, ice cores, and cave deposits across multiple continents, reconstructed the atmospheric consequences of the Lachamps excursion in unprecedented detail. What they found was alarming. With the magnetic field at 5% of its current strength, the cosmic ray flux reaching Earth's surface increased dramatically. Cosmic rays, high-energy particles from outside the solar system, normally deflected by the magnetic field, penetrated the atmosphere in far greater numbers. This increased cosmic ray flux produced elevated levels of carbon-14 in the atmosphere, detectable in tree ring records, and elevated levels of beryllium-10 in ice cores. The increased radiation also affected the chemistry of the upper atmosphere. Ozone depletion, driven by the interaction of cosmic rays with atmospheric chemistry, occurred on a significant scale. The protection against ultraviolet radiation that the ozone layer currently provides was reduced. The Cooper paper also identified changes in the climate record coinciding with the Lachamps excursion, shifts in temperature, precipitation patterns, and vegetation zones that were not fully explained by orbital or solar forcing alone. Some of these climate changes were regional, others appeared to be global in extent. And then there was the human record. Approximately 42,000 years ago, right at the time of the Lachamps excursion, the archaeological record of human activity in Europe shows a significant disruption. The Neanderthals, who had inhabited Europe for hundreds of thousands of years, disappeared from the fossil record. The earliest cave art in Europe appeared. The woolly mammoth population underwent significant stress. The megafauna extinctions that characterize the end of the Pleistocene appear to have accelerated. The Cooper paper proposed that the Lachamps excursion, through its effects on radiation levels, ozone depletion, and climate, was a significant contributing factor to these changes. Not the sole cause, not a simple kill mechanism, but a global environmental stressor that altered conditions for every species on Earth during its approximately 1,000-year duration. This proposal is contested. Correlation does not establish causation. The 42,000-year period was also characterized by significant glacial advance and solar output variations that provide alternative explanations for some of the observed changes. But the correlation exists, and it is specific enough and the physical mechanism plausible enough that the Lachamps excursion has moved from geological curiosity to serious consideration as a factor in one of the most significant periods of human and megafaunal history. The 2021 Cooper et al. Paper in Science, titled "A Global Environmental Crisis 42,000 Years Ago," analyzed records from New Zealand kauri trees preserved in swamp deposits, providing a precisely dated atmospheric record spanning the Lachamps excursion. The kauri tree record showed a 12-fold increase in atmospheric radiocarbon production during the excursion, consistent with a dramatic increase in cosmic ray flux during the period of extreme field weakness. Now translate the Lachamps scenario into contemporary terms. During the Lachamps excursion, the human population of Earth was in the tens of thousands. There were no satellites, no electrical grids, no GPS systems, no internet infrastructure, no communication networks, no financial systems dependent on electronic data integrity. The primary impact of elevated cosmic radiation and ozone depletion on Paleolithic humans was biological. Increased radiation exposure, altered climate, disrupted food chains. The technology of the time, stone tools, fire, shelter, was not vulnerable to electromagnetic disruption. Your world is. Approximately 5,500 satellites currently orbit Earth. The global financial system processes trillions of dollars in transactions per day, all dependent on electronic infrastructure. Aviation navigation systems rely on GPS and magnetic heading references. Power grids spanning continents are managed by systems that depend on electronic control. The internet, the communication infrastructure of modern civilization, is carried by subsea cables, radio transmissions, and satellite links. Every one of these systems has a vulnerability to the conditions that occur during a geomagnetic reversal or excursion. Satellites in low Earth orbit are currently partially protected by the magnetic field from the most energetic particles in the solar wind and cosmic ray flux. During a reversal, with the field at 5 to 10% of its current strength, that protection is dramatically reduced. Single event upsets in satellite electronics, caused by energetic particles passing through semiconductor components and flipping bits, would increase dramatically in frequency. Power grids are vulnerable to geomagnetically induced currents, electrical currents induced in long conductors by rapid changes in the magnetic field during geomagnetic storms. The 1989 Quebec blackout, which left 6 million people without power for approximately 9 hours, was caused by a geomagnetic storm of moderate intensity. The March 1989 storm had a DST index of approximately negative 589 nanoteslas. The Carrington event of 1859, the largest geomagnetic storm in the modern record, is estimated to have been several times more intense. During a reversal, the compromised magnetic field would make Earth far more vulnerable to the effects of even moderate solar activity. Events that currently produce regional power disruptions could, during a period of extreme field weakness, produce disruptions on continental or global scales. This is not speculative. The physical mechanism, geomagnetically induced currents in power grid conductors, is well understood and has been documented in multiple events. The question during a reversal is not whether it would happen, but how frequently and at what scale. Stop here for a second. The 1989 Quebec blackout, 9 hours, 6 million people, caused by a moderate geomagnetic storm. During a reversal, the field protecting us from those storms would be at 5 to 10% of its current strength. What do you think happens to a modern city during a blackout that lasts not 9 hours, but 9 months? Drop your answer below. The infrastructure analysis is in the next section. Let's go through the infrastructure vulnerabilities systematically, because the list is longer than most people realize, and the interdependencies are more complex than a simple enumeration suggests. Start with GPS. The Global Positioning System and its equivalents, Russia's GLONASS, Europe's Galileo, and China's Beidou, depend on satellites that transmit precise timing signals used to calculate position. These satellites are in medium Earth orbit at altitudes of approximately 20,000 kilometers. At this altitude, they are partially protected by the magnetic field, but exposed to significant radiation during geomagnetic storms. During a reversal, two things happen to GPS systems. First, the satellites experience higher radiation environments that increase the rate of electronic component degradation and single event upsets. Second, and more significantly, the ionosphere, whose electron density is influenced by the magnetic field's interaction with solar wind, becomes more variable and unpredictable. GPS signals pass through the ionosphere, and variations in electron density introduce errors in the timing signals. Currently, these ionospheric errors are well characterized and corrected for. During a reversal, with a chaotic, weakened field producing a more variable and less predictable ionosphere, the corrections become less reliable. GPS positioning errors during intense geomagnetic storms are already documented. Errors of tens to hundreds of meters in severe cases, compared to the sub-meter accuracy of normal operation. During a sustained period of compromised field, these errors would be persistent rather than episodic. Aviation depends on GPS for navigation, approach procedures, and automatic dependent surveillance. Maritime navigation uses GPS for vessel tracking, collision avoidance, and port approach. Precision agriculture uses GPS-guided equipment that operates to centimeter accuracy. Financial systems use GPS timing signals for transaction synchronization across distributed networks. None of these systems would stop working entirely during a reversal, but all of them would operate with reduced reliability, increased error rates, and higher maintenance requirements during a period of sustained elevated radiation and ionospheric variability. Now consider the power grid. Modern power grids are continent-spanning networks of transmission lines connecting generation sources to consumers. The lines themselves are long conductors, exactly what geomagnetically induced currents require. During geomagnetic storms, fluctuations in the magnetic field induce quasi-DC currents in these lines. Currents that flow in the wrong direction, at the wrong frequency, and saturate the cores of the large transformers that are critical nodes in the transmission network. Transformer saturation causes overheating. Overheating causes damage. Damaged transformers, particularly the large, custom-built, high-voltage transformers that are central to grid operation, take months to years to replace. They are not stockpiled, they are manufactured to order. There are approximately 2,000 high-voltage transformers in the North American grid, each weighing hundreds of tons, each custom-designed, each with a delivery lead time of 12 to 18 months under normal manufacturing conditions. During a severe geomagnetic storm, the kind that occurs multiple times per solar cycle, but is currently largely manageable due to the existing field strength, multiple transformers could fail simultaneously. During a reversal, when the field is too weak to protect against even moderate solar activity, transformer failures could accumulate faster than they can be replaced. The 2008 National Academy of Sciences report, Severe Space Weather Events, Understanding Societal and Economic Impacts, estimated that a Carrington-level geomagnetic storm could cause grid outages affecting up to 130 million people in the United States alone, with restoration times of 4 to 10 years due to transformer supply chain limitations. 4 to 10 years without power for 130 million people from a single severe geomagnetic storm under current field conditions. During a reversal, the field conditions that make a Carrington-level event catastrophic would be the baseline. Every moderate solar storm would carry Carrington-level risk to a civilization whose infrastructure was designed for a full-strength magnetic field. Now consider radiation exposure. Earth's atmosphere provides a significant additional layer of radiation shielding, equivalent to approximately 10 meters of water in terms of radiation protection. This shielding is currently supplemented by the magnetic field's deflection of charged particles before they reach the upper atmosphere. During a reversal, the magnetic contribution to radiation shielding is reduced. The atmospheric contribution remains. The result is a radiation environment that is elevated but not immediately lethal, not like being in deep space, where there is no atmospheric shielding, but elevated enough to matter for long-duration exposure. At high altitudes, where the atmospheric shielding is thinner, the increase in radiation would be more significant. Airline crew, who currently receive approximately 3 to 5 millisieverts of radiation per year from cosmic rays during high-altitude flights, would receive higher doses during a reversal. Frequent flyers would receive higher doses. The current regulatory limits on occupational radiation exposure for aircrew might need to be reconsidered. For the general population at ground level, the radiation increase during a reversal is estimated to be manageable, a significant increase above baseline, but not at levels associated with acute radiation sickness. The primary concern is the increase in cancer risk from elevated chronic exposure over the centuries to millennia duration of the reversal process. During the Lachamps excursion, when the field reached 5% of its current strength, the cosmic ray flux increase was sufficient to produce measurable effects on atmospheric chemistry and tree ring records. The ozone depletion associated with the event was regional to significant. Whether the current ozone chemistry program, already stressed by anthropogenic chlorofluorocarbons, would respond the same way is uncertain. The 2008 National Academy of Sciences report on severe space weather was commissioned by NASA and produced by a panel of experts in space weather, power systems, and national security. It estimated direct economic costs of a Carrington-level event at approximately $1 to $2 trillion in the first year, with full recovery taking 4 to 10 years. The report noted that the most vulnerable component of the power grid is the large, high-voltage transformer, of which there are approximately 300 ultra-high voltage units in the United States, none of which are stockpiled as spares. The honest answer to the question of when a geomagnetic reversal will occur is, we do not know. Not, we have a rough estimate. Not, we know the general time frame. We genuinely do not know. The geomagnetic reversal process is driven by the fluid dynamics of the outer core, a system that is turbulent, chaotic, and impossible to predict on the timescales relevant to human civilization. What we can say is the following. The current rate of field weakening, if continued linearly, would produce a field collapse within approximately 1,500 to 2,000 years. But the weakening is not linear. Historical excursions and reversals show that the field can weaken rapidly, reaching minimum values in centuries rather than millennia, or can stabilize and recover without completing a reversal. The current geomagnetic changes, the weakening field, the accelerating pole movement, the growing South Atlantic anomaly, the reversed flux patches on the core mantle boundary, are all consistent with the early stages of either an excursion or a full reversal. They cannot be distinguished at this stage. If it is an excursion like Lachamps, the minimum field strength could be reached within centuries, and recovery could occur within 1,000 years. If it is a full reversal, the process could take anywhere from a few thousand to tens of thousands of years. The Matuyama-Brunnis reversal, the last full reversal, 780,000 years ago, appears from the paleomagnetic record to have occurred rapidly by geological standards, within approximately 4,000 years. Some paleomagnetic studies have suggested that portions of the transition may have occurred even faster, within centuries. A 2014 paper by Singer and colleagues analyzing volcanic rocks from multiple locations that recorded the Matuyama-Brunnis reversal found evidence that the transition included a period of extremely rapid field change, potentially as fast as 1 degree of pole movement per year for a sustained period. If correct, this would mean that the most dramatic phase of a reversal, the period of most extreme field weakness and pole chaos, could develop faster than previously assumed. Faster than previously assumed. On timescales relevant to human infrastructure planning, what can we do about this? The honest answer is, not much about the reversal itself. You cannot prevent a geomagnetic reversal. You cannot stop the fluid dynamics of the outer core. You cannot maintain the field artificially. The geodynamo operates on a scale and at an energy level that is entirely outside human influence. What you can do, what civilization could do, if it chose to prioritize this, is harden the infrastructure against the conditions that a reversal produces. Power grids can be equipped with geomagnetically induced current blocking devices, filters that prevent the quasi-DC currents from reaching and saturating transformer cores. These exist. They are commercially available. They are not widely deployed because the cost of widespread deployment is significant, and the event being prepared for seems distant and uncertain. Satellite systems can be designed with higher radiation tolerance, using radiation-hardened components, redundant systems, and increased shielding. This adds cost and mass to satellite designs. Currently, most commercial satellites are not built to the radiation tolerance standards that would be required during a reversal. Spare transformers can be stockpiled. The United States government has discussed this. The SHIELD Act, first introduced in Congress in 2012, proposed a program to stockpile spare high-voltage transformers for exactly this purpose. It has not been fully implemented. The gap between what could be done and what is being done is not a technical gap. It is a priority gap. The reversal is real. Its consequences are understood. The infrastructure vulnerabilities are documented. The preparations are available. They are not being made at the scale required. Geomagnetically induced current blocking devices, also called GIC blockers, are installed at selected substations in Finland, Norway, and South Africa, countries with high geomagnetic storm risk due to their high latitudes or proximity to the South Atlantic anomaly, respectively. The Finnish power company Fingrid began installing GIC monitoring and mitigation systems in the 1990s, following observed geomagnetic storm impacts on the Finnish grid. The cost of equipping the entire North American high-voltage grid with equivalent protection has been estimated at several $billions, a fraction of the estimated cost of a major grid failure. Let's come back to where we started. Right now, as you finish watching this, something is protecting you. The same thing that was protecting you when you started. The magnetic field of Earth, the geodynamo that has operated continuously for 3.5 billion years, is deflecting the solar wind, shaping the ionosphere, limiting the cosmic ray flux that reaches the surface. It is doing this less well than it was 200 years ago, approximately 9% less well by the measure of total dipole moment. The north magnetic pole that your phone uses to orient its compass is approximately 2,000 kilometers from where it was in 1900, moving at a speed that required an emergency update to the global navigation model. These are measurements. They are not predictions. They are not models. They are observations of something that is happening right now, today, in the liquid iron of Earth's outer core. Whether what is happening right now is the beginning of an excursion that will recover within centuries, or the beginning of a full reversal that will take thousands to tens of thousands of years to complete, cannot be determined with current science. What can be determined is this: the conditions associated with the most dramatic phase of either scenario, the phase when the field is at its weakest, when the poles are most chaotic, when the cosmic ray flux is highest and the ionosphere is most variable, are conditions for which modern technological civilization has no serious preparation. The GPS systems you use for navigation, the power grid that runs your home, your hospital, your water treatment plant, the satellites that carry the communication infrastructure of the global economy, the financial systems that process every transaction you make, all of it was designed and built under the assumption of a full-strength magnetic field. None of it was designed for the conditions that occur during a geomagnetic reversal. The reversal, if it is coming, is not coming tomorrow. It is not coming this decade. The geological timescales involved give civilization centuries to millennia of warning. The question is whether the civilization that receives that warning will use the time it has. The 1989 Quebec blackout lasted 9 hours. The transformer survived. The grid came back. During a reversal, the storm that caused the 1989 blackout would be a routine event in a world where the baseline protection had dropped by 90%. 9 hours is a crisis. 9 months is a civilizational event. The shield is weakening, the data is public, the preparations are available. What happens next is, in a very specific and literal sense, a choice. The magnetic field of Earth has reversed 183 times in the last 83 million years. Every species alive during those reversals experienced the reduced field. Most of them survived. Life on Earth survived. The biosphere survived. What has never experienced a geomagnetic reversal is a civilization that depends on satellites for navigation, on continental power grids for survival, on semiconductor electronics for the management of food distribution, water treatment, and medical care. We are the first. The Lachamps excursion lasted approximately 1,000 years, at 5% of current field strength, in a world of Paleolithic humans with stone tools. Modern civilization has existed for approximately 10,000 years. The power grid has existed for approximately 140 years. The internet has existed for approximately 50 years. GPS has existed for approximately 45 years. These systems are not old enough to have experienced a geomagnetic excursion. They have never been tested by one. We do not know how they fail or in what sequence, or whether partial function is maintained, or whether the interdependencies produce cascading failures that are worse than the sum of individual component failures. We do not know, because it has never happened. What we know is that the field is weaker than it was, that the poles are moving faster than they were, that the South Atlantic anomaly is growing, that the reversed flux patches on the core mantle boundary are consistent with what computational models show in the early stages of a transition, and that the systems you depend on for everything were not built for what comes next. One question: if the geomagnetic reversal process is already underway, if the field reaches its minimum within the next 500 to 2,000 years, which single piece of modern infrastructure do you think fails first and causes the most damage? GPS, power grid, satellites, financial systems, or something else entirely? Drop your answer below. I will address the most interesting ones in the next video. Next video. What are quasars, objects so luminous they outshine entire galaxies of 100 billion stars, powered entirely by matter falling into a black hole, and why the early universe was filled with them in a way that tells us something deeply unsettling about where the universe is going? See you there.